Good morning.
Good morning.
Shoot. Looks like it's getting a little harder for people to get up for first period. Trickling in a little late.
No.
Hey guys, how's everybody doing? Doing all right? All right. I guess from yesterday we didn't quite finish the last little bit of the notes, so I'm going to finish that, and then today's I think is a little shorter, so hopefully we should be all caught up and things, and be able to leave at a normal time with all of our notes and stuff done. So I guess I will get started. Let me see here. Hopefully I notice if anybody tries to come in late. I'm not too good at remembering to check that out once I start. All right, I think yesterday we stopped with projections. And I could tell because I got an email or two from a couple of people that were a little confused. This is not the projection formula up here. Okay, this is related to where it comes from, is if we just did use that dot product formula, it's related to where it comes from. This is the formula for how to do a projection. So don't use the thing I wrote in green to try and do a projection. I was just pointing out that they're very similar looking because they are related. This can be proven using trigonometry, which is similar to what we've got there with our projection formula. So, with our dot product formula, the thing in green. So that's a formula you guys should use. And I think I did this one example, I did it very fast. So didn't probably get a chance to really see what we were doing, but this is the u dot v is up here. So I just went component by component, 3 times 7, -5 times 1, 2 times -2, and that was up there. And then this is the magnitude of v squared here. So I just went through and squared all the components and added them together, and then times v, and then I just simplified. So here's my projection down here. And then if you subtract from u, you'll get the other piece. So we have u, we have v, u, we have w1, which is the part parallel to v. V would be down here as well. In this case, I think v is actually longer. And then we get w2 by just subtracting, because w1 plus w2 equals u. It's like head to tail already there. Okay, so I used a bunch of boat examples yesterday, so this is basically that same idea. You have a boat sitting on a ramp inclined at 30 degrees. So like this would be the ramp, 30 degrees. What force is required to keep the boat from rolling down the ramp? So if you have a boat up here, my excellent art skills. If you have a boat up here on the ramp, you basically have a force F. It's going to be going down like this. F is just the mass of the boat, right? The gravity's effect on the boat. That's kind of our main force there. And if you think of gravity, it's going to pull straight down. So there's going to be no horizontal component. And then we're pulling down at 600 pounds. So you'd have a -600 right there. V would be the ramp itself. Okay, so V we're looking for a vector going parallel to that ramp. It doesn't really matter the length of it. I'm just going to choose a unit vector because that's the easiest thing. So remember, if we think on the unit circle, any vector going in the direction 30 degrees is what we want, we can just use cosine 30, sine 30. Which is root 3 over 2 and then 1/2. Got a late person here. Hold on.
Should be allowed at this.
Yeah. So we have our V, we have our F. So all we do to get our projection there, this is basically the U in the projection formula. We're going to use the F. U stands for like kind of the main force, the resultant that we're trying to break up. And in this case, it's the mass of the thing. So that's what we're going to use as our U. So our W1, our projection of F onto V, we'll do F dot V of the magnitude of V squared times V. So if we do F dot V, we'll have 0 times root 3 over 2 and negative 600 times 1/2. So we'll have negative 300. The magnitude of V, well, we have it's a unit vector. We chose a unit vector. So the magnitude of V is 1 here. But if you wanted to do the square of both of those things and add them together, you'll have 3/4 plus 1/4 is 4/4. So the magnitude here is 1 times V itself. So we have negative 150 root 3 and then negative 150. And if we find the magnitude of that, that's how much of the 600 pounds is actually pulling down the ramp. So if we found the magnitude of that thing, it will end up being 300. Okay, if you have a calculator, you can use a calculator if you want on bigger stuff like that. But 300 pounds. Okay, so out of that 600 pounds, only 300 is pulling down the ramp. So if you pull with more than 300 pounds of force up, you'll at least 300 to hold the boat steady. More than that would pull the boat up the ramp. Okay, and it doesn't ask about the other force, but if you wanted the other force, you just subtract F minus W1 and you could get the W2, the portion pulling into the ramp. Okay, last thing is work done, I think is the last thing, is work done by a force acting on an object. So as long as it's acting in line of motion, so say this box is being moved this way. If the force is acting in the exact same direction, you would just multiply the magnitude of the force times the distance. So PQ represents the path of the object. The magnitude of PQ would basically be how far you moved it. So work done in moving the object would be magnitude of the force times the distance that you moved, as long as you're going in that direction, which is not common. A lot of things that's not the case, but that's how you could find work done. Generally, we need a formula that can encompass more motion. So if the force is not necessarily along the line of motion, so like picture a wagon. Okay, like if you're a kid and you have a wagon and the handle's up here, generally when you're pulling the wagon, you're not pulling it horizontal or parallel to the motion of the wagon. It's kind of got a little hinge on it, so you're able to pull it at different angles. So if it's not along the line of motion, we would actually want only the portion of the force that is in line with the motion. So again, F is really going to have some horizontal piece that's moving along the path, and so, some of the force, if you're pulling at that type of an angle, some of the force is lost this way. So if you're pulling with 20 pounds of force on the wagon, but it's at an angle, really 20 pounds of force is not pushing the wagon forward. Part of it's being lost in that vertical piece. So we would normally, by definition, okay, this is the definition. of work done. So it's kind of like in calculus when we learn like definition of derivative, definition of whatever, all sorts of things. We didn't actually use that to find it. This is really what we mean by work, but we have a simplified way of finding it. Oops, except my iPad froze. No, there we go. Is instead of having to find the projection and find those magnitudes, if we just do F dot PQ, the dot product, we'll get the same thing. Okay, and that's basically what would happen if we plugged in. You could pretty easily prove it if you plug in the projection formula that we just learned, and you plug in all the stuff, and then you just simplify. And what you'll see is what's left is a dot product. So we can actually find it pretty easily by just taking a dot product. So that's what we would actually use. To find work done is just a dot product. So they're actually pretty simple problems. If you use the definition, you should get the same thing, but you're gonna do more work. So say this guy is closing a barn door, a sliding barn door. And so he's got this rope that he pulls on that's attached to the door, and he just walks this way and the door slides shut. And we're looking at, he's pulling with 50 pounds of force and an angle of 60 and just kind of walking straight across. What is the work done then on moving the door 12 feet, which let's say it's 12 feet wide, so that'll close the door. Okay, so what we want is the force, so basically the force being exerted on that rope. So in this case, again, usually I would use the magnitude, 50, times the unit vector that's moving in the same direction. So if you think about the unit vector in this picture right here, that would be going 60 degrees that way. Well, unit vector, unit circle goes counterclockwise. So we're actually kind of going down. So you could either use 300, which would be going counterclockwise, or we could use negative 60. Since the force is being exerted kind of in that downward motion. And so that would be a unit vector going in the direction of the force times a magnitude. So it'll be the correct magnitude that we're looking for. And again, these are values we should know. 1/2 and negative root 3 over 2. So we could simplify this. This is 25 and negative 25 root 3. So that's the vector of the rope that the guy's pulling on, basically, the force that's associated with that. PQ is the path of the door. So while he's pulling on that rope, the door is just moving horizontally across. It's on the little sliders. So since it's moving horizontally 12 feet, the path of the door is 12, 0, right? Because it's going to move straight across. It's not going to move up and down. And so if we want work, we just do F dot PQ. So we'll have 25 times 12 plus a negative 25 root 3 times 0. So we'll have 300. And I think it's foot-pounds of force. We're taking the feet that the door is moving times the pounds that are being exerted on it. And that, so usually work is some sort of like a force times a distance, units wise. Again, this is all stuff you probably, if you're in physics, you'll probably see something similar when you guys, if you haven't already, in physics stuff. So a lot of times you'll have had a better physics explanation, and some of you guys probably can explain it better than me, because I took a lot of math and not a lot of physics. So yeah, so that's work done. Pretty simple. Again, I don't really make you memorize formulas. So as long as you have it written somewhere that's easily accessible and you understand how to use it, on your test, you can use your notes. So don't have to memorize that. Okay, we're gonna go to what was supposed to be today, which is cross products. Okay, so we talked about dot products yesterday. Cross products is another type of multiplication. It's more complicated. So the main idea, so with dot products, I would say the main purpose of a dot product is it gives you angle information. Okay, the main idea of a dot product, it's appearing in a formula. It's because you're trying to get some information about the angle between vectors. With a cross product, what we're going to get is a vector that's orthogonal to two other vectors. So it's hard to show because it's three-dimensional, but say I have two vectors in space. Well, then what I'm wanting is a vector that's perpendicular to this one and to this one. So picture like you have the X and Y axis, and we want the Z axis. Okay, but that could be tilted anywhere in space, and they don't have to all be perpendicular to each other. You just take any two vectors, and we want the third one that's perpendicular to both. So this is only really applicable in 3D space. Okay, but that's going to be the main point of the cross product. It does appear in other formulas and stuff, but it kind of at its most basic level, that's the information that you're getting when you take a cross product, is you're getting a vector that's perpendicular to the two things you multiplied. Okay, so we have the dot product. It yields a scalar. Okay, remember it yields a number. Dot product gives you information about angles. Cross product will yield a vector. Okay, sometimes it's called a vector product because it yields a vector, and that vector is orthogonal to the first two. So like if I do a cross product, W will be orthogonal to both U and V. Okay, you'll have found a perpendicular vector. Perpendicular is a big theme of actually both this course and linear algebra. Is the idea of orthogonality is kind of important. If you really think about like our graphing system, it's all based on right angles. If somebody hadn't decided that the X, Y, and Z axis are all perpendicular, graphing would be really hard. So there's reasons that we want that. Okay, and so cross product, what's going to happen is we get what looks really complex and like something you wouldn't want to have to memorize. So say that these are U and V and we want to take the cross product. Well, what we're going to get is U2 V3 minus U3 V2 times I, and then minus U1 V3 minus U3 V1 times J, and then plus U1 V2 minus U2 V1 K. Okay, and that would be the cross product. So you're going to basically multiply a bunch of components together, subtract them, and all this stuff. Really where this comes from is a determinant. So if you think back to Algebra 2, again, you guys didn't spend a bunch of time on this, but way back in Algebra 2, you probably did determinants for like a day or two. In linear algebra, we do them a lot. And this course used to come after linear algebra, and then for some reason the school decided to switch them. But without going too much into it, basically what we're going to do is we're going to kind of treat this as the determinant of a 3x3 matrix, where the first row is just I, J, K. The second row are the components of vector U. So U1, U2, U3. And then the next one is the vectors, the components of V. So V1, V2, V3. Okay, and we go to take the cross product, we're taking a determinant. You're basically going to for the I component, okay, the I component of the cross product, you're going to ignore everything in the same row and the same column as I, and it's made of multiplying across this way and subtracting. So notice it's U2 V3, U2 V3 minus U3 V2. Okay, so that's how you'd take a determinant, is you'd start with, well, you can really start anywhere. In this case, we're always going to start with I, and then the four values that are not in the same row and column as I, we basically multiply across and subtract. And then you move over, and J, we would ignore the stuff in the same column in the same row as J and do the same thing. And notice I have U1 V3 and U3 V1 are my little components that make up the J. Also notice it alternates signs. So this one's positive, negative, positive. So as we go across, the signs change each time. And then for that last piece, for the K component, we ignore the stuff in the same row and column, and then we'll have U1 V2 and U2 V1. So I'll kind of show you when we do the examples how I do a cross product as quickly as possible, like not having to write out all this stuff and not having to memorize this formula. I'll kind of show you what I usually do. It's easier if I could be there and point at it because that's what I'm used to doing, but I can't. So that's how you get a cross product. And again, now this vector here, this will be one single vector. Those are just a bunch of numbers you'd add together. This vector here would be perpendicular to U and perpendicular to the V. Okay, so we could show that. Remember, we can tell if things are orthogonal using a dot product. So we could take that vector that we just had, U2 V3 minus U3 V2, and I might move it down because I think I'm going to run out of room if I do it there. Minus a U1 V3 minus U3 V1, and then U1 V2 minus U2 V1. Okay, that's our cross product vector. If we multiply that by either U or V, it doesn't really matter. Remember that yesterday, the dot product, if they're orthogonal, the dot product should be 0. So if I take the dot product there, I'll get U1 times U2 V3 minus U3 V2 minus U2 times U1 V3 minus U3 V1, and then plus U3 times U1 V2 minus U2 V1. And if I go ahead and use my distributive property and simplify that all down, I have U1 U2 V3 minus U1 U3 V2 minus U2 U1 V3 plus U2 U3 V1 plus U3 U1 V2 minus U3 U2 V1. And hopefully I didn't make a mistake there and lose anything. So do I see, here's U1 U2 V3 and a minus U1 U2 V3. And then here's U2 U3 V1 and a minus U2 U3 V1. And then I have U1 U3 V2 and a minus U1 U3 V2. And so notice our dot product will give us 0. Okay, you could do the same thing with vector V and show that the dot product of the cross product and V would also give us 0. So that's kind of proving that what we're getting is going to be orthogonal no matter what all those U's and V's are. We're going to get something that's orthogonal to both. Okay, just like I've been saying, we're going to go over some of the properties of cross products. It's not commutative, meaning order matters. So if I multiply U times V or V times U, I will actually get something different. They are related. You'll still, if I do V cross U, I'll still get one that's orthogonal. It'll just be going the opposite direction. So you don't really want to interchange them, although they will give you similar ideas. So think like in one direction, if I did a vector on the x-axis and the vector on the v-axis, if I multiplied in one direction, I would get a vector on the z-axis maybe going positive, and if I did the other direction, I would get one going negative. They'll both be perpendicular, but you can't just switch them whenever you want. It's going to change the sign. So order is going to matter. You can do the distributive property with addition. but order matters. So when I distribute, if I'm doing U times that sum, I need to keep U on the left side. So this will be U cross V plus U cross W. Versus if I did, oops, the cross product on this side. When I distribute, it should stay on the same side. Right, so order matters, but otherwise distributive property is fine. Scalar, kind of like the dot product, just make sure since you're multiplying, we want to either multiply U or V times C. You don't want to multiply both. So you could either think of this as CU crossed with V or U crossed with CV, but you don't want to distribute the C onto both. Okay, again, think with normal arithmetic. If I had 2 times 4 times 5, that's either 8 times 5 or 4 times 10. It's not 8 times 10. I wouldn't want to distribute the 2 twice. You just do it to one of them. Okay, the cross product with 0 does give me the 0 vector. Cross product with itself. So if I cross a vector with itself, I will also always get the 0 vector. Okay, the problem there is usually, like if you think of 3D space, if I've got 2 vectors in space, there's really one direction that's perpendicular, and it's going to go, kind of through the 2 vectors, either up or down. But if I've got one vector in space, I've got lots of things perpendicular to that. So if I try to find a vector perpendicular by doing a cross product with a vector in itself, I don't have kind of the necessary information. I could get all sorts of vectors that are kind of like perpendicular going in all directions. Okay, if we want to mix dot products and cross products, we can take the dot product of a cross product, right? Because V cross W is a vector, so we could dot product with that vector. This is the same as doing U crossed with V and then dotting with W. Okay, so if I kind of try to adjust the parentheses, the cross product has to happen first. If the dot product happens first, you lose a vector and you can't do the second operation. Kind of like when we tried to look at taking multiple dot products yesterday. You can't do U dot V dot W because once you do U dot V, that vector is gone. So same idea here, you can't do the dot product first and then a cross product because the cross product requires a vector. Okay. They also have some geometric properties. So I call those as algebraic properties. Here, this looks very similar to the thing we did with dot products. With cross products, we'll have a sine instead of a cosine. And so the magnitude of U cross V is equal to the magnitude of U times the magnitude of V times sine theta. And that actually comes from that last thing, and I'll show you a picture of where it comes from there. U cross V will equal 0 if U and V are scalar multiples. So like if U and V are running either the same direction or opposite directions, if I take a cross product, I'm going to get 0. So that kind of comes also from one of the properties on the previous page. If U is a multiple of V, and I'm trying to do U crossed with V, that's the same as CV crossed with V, which is the same as C V cross V, which is going to be C times 0. That's a property from the other page, is if I multiply by itself. So even if I multiply by a multiple of itself, you're going to get 0. Okay, and that last one is if I have a parallelogram that has sides U and V, then I can get the area of the I can get the area of the parallelogram by taking a cross product of those. And that's actually where that first property also comes from. If we think of the angle between the vectors as theta, normally with a parallelogram, we want base times height. So if I look at trying to find this height, I could use trigonometry. Right, sine of theta is opposite. So this, we'll call it h, opposite over the hypotenuse, which means h will be the magnitude of u times the sine of theta. And so if I just did area equals base times height, the base is the magnitude of v, and the height is the magnitude of u sine theta. So we can find the area of a parallelogram by just taking the cross product of u and v and not having to find the height at all. It's also showing this relationship up here. Again, you don't have to memorize this stuff. You just want to have it somewhere where you can use it and find it and things like that. Okay, so that's kind of the main stuff. So we have, I think, a few examples and then we're done. So find a unit vector orthogonal to both u and v. Okay, so first thing is I'm going to find something that's orthogonal to both u and v. The way we do that is with a cross product. So the way I usually do that is I just take u and then I write u and v one over the other. So I'm going to write v down here. It's 2i plus 3j. Since it doesn't have a k, that's implying k is 0. Okay, in 3 dimensions, a 2-dimensional vector just has 0 as the other component. And then I just go down, and if I'm trying to figure out what u cross product of u and v are, I kind of go down the line, and instead of writing out the thing to do the determinant, the first one, I just think about multiplying these numbers. And so I do it in my head. You might want to write it out at first, but you do -4 times 0 minus a 1 times 3, and that's your I component. And then remember the next one changes sign, so I have minus. Then I just move this over here and do the same idea. So I'm going to multiply 1 times 0 minus 1 times 2. Okay, the number's kind of going across there, and that's my j component. And then the next one I change back to positive, and I'm basically just sliding this down. And if I go across with those 4 numbers there, I have 1 times 3 minus a -4 times 2. And that's my k component. And then I just simplify what I've got. So I've got a -3i. I've got a minus 2, so a plus 2j. And then I have 3 minus a -8, so 3 plus 8. So I have plus 11k. And then that's my vector that should be orthogonal to both u and v. If you want to double check, just a dot product is easy. So think if we were to dot these vectors together, I have -3 times 1. I have 2 times -4. And then I have 11 times 1, and I get 0, which is what I want, right? If I quickly just looked at a dot product, I'm going to get 0 with u. And then if I did the same thing with v, I'd have -3 times 2, and then 2 times 3, and then 11 times 0, and I get 0. So I can quickly verify that is orthogonal to both. If I take a dot product, I'm going to get 0 both times. Okay, so it's easy to make a mistake doing a cross product, but it's somewhat easy to find that mistake. Okay, so that's answering the orthogonal piece. Notice it wants the unit vector. So what I'm going to need is I'm going to need the magnitude of u crossed with v. So I'm going to take the square root and then square each of the components and add them together. So -3 squared is 9, 2 squared is 4, 11 squared is 121. And then if I add that all together, I have the square root of 134. So that's the magnitude of u crossed with v. It's pretty big. So my unit vector going in the same direction, perpendicular, would just be 1 over the square root of 134 times -3i plus 2j plus 11k. Same direction. It's just that that one's a unit vector. The other one is very long. Okay, so that's kind of the basic idea of a cross product. Again, the basic information you get is perpendicular stuff. Right. So again, this has some geometric application. So if we have quadrilateral ABCD, we could show that it's a parallelogram. Using vectors. We actually had to do this in geometry all the time, but we could use vectors. So what I would do is I would find the sides AB, BC, CD, and AD. And again, remember, this is from lesson number 1. All you do is subtract the terminal point minus the initial point. So to find AB, we'll do B minus A. So 2 minus 5 is -3. 6 minus 2 is 4. 1 minus 0 is 1. And it technically wouldn't really matter if you did BA instead. Okay, it's going to come out the same idea. CD, I'll do 5 minus 2 is 3. 0 minus 4 is -4. 6 minus 7 is -1. BC, I'll do 2 minus 2 is 0. 4 minus 6 is -2. 7 minus 1 is 6. And then AD, 5 minus 5 is 0. 0 minus 2 is -2. And 6 minus 0 is 6. And so you should already be able to see it's a parallelogram, right? Opposite sides are parallel. So AB is parallel to CD. And BC is parallel to AD, since they're scalar multiples. So ABCD is a parallelogram. Okay, find its area then. We're going to do adjacent sides. You could pick any 2 adjacent sides. So like AB crossed with BC. Okay, and I already have one written over the other. So I'm going to use these 2 up here. And I'm going to do what I did before. Basically, I just cover up, and it's hard to kind of do that on this page. I just cover up the X components. Oops, not erase. Cover up the X components. And then I kind of multiply across what the components are that's left. So I'll have 4 times 6 minus 1 times -2, I. And then just move across. And I have a minus -3 times 6 minus 1 times 0, J. And then I just move across. And then I have a -3 times -2, oops, minus 4 times 0, K. So 24 plus 2, I have 26i. And then, let's see, negative 18, but a negative 18, so plus 18j. And then I have a 6 minus 0, so plus 6k. Okay, that would geometrically just represent a vector coming off the page perpendicular to the page. Wherever this thing is graphed, it's just perpendicular to the parallelogram. But if we find the magnitude of that, square root of 26 squared plus 18 squared plus 6 squared. Okay, that's going to give us area. So pretty large. I don't have a calculator, but you could use a calculator on something like that. Now I keep forgetting, what time is this class supposed to be over? Because yesterday I let you guys out really late. 35. Oh, we are going to run out of time. Dang it, I thought I was going to have enough time now. Okay, so is it a rectangle? We could use vectors to show that. This is the same points, so we don't have to show, we already know it's a parallelogram. Okay, we already have that it's a parallelogram. So if you think back to geometry, all we need is two sides to be perpendicular. And we would know that it's a rectangle. Okay, if we have a parallelogram with perpendicular sides, that means that it's a rectangle. So all we need to do is show that AB dotted with one of its adjacent sides is 0. So we have 0 minus 8 plus 6 is 2. So not perpendicular, so not a rectangle. Okay, if you hadn't shown it was a parallelogram, we would have to show all 4 angles are right angles, but since it's already a parallelogram, if one of the angles is a right angle, that means all the other ones are too. In this case, it's not though. If we didn't get 0, so it's not perpendicular. Right, and there's other ways to show rectangles and things like that too. Okay, we can find torque. This is the last application, so we'll at least get to the explanation of it. We might not get to the final example. So torque, for us, we're going to use what's called the magnitude of the moment, which is the tendency of a vector to rotate about its axis. So think like if I have a lever and I push on the lever, it's giving me the tendency, like if I push on at this angle, or if I push at this angle or whatever, it's the tendency of that lever to want to turn. So like if my lever looks like this and I push with a force here, it's not going to want to turn at all. Right? But if I push with a force here, it may want to turn. If I push at a force at an angle, it's probably going to want to turn less, right? If it's at perpendicular, it wants to turn a lot. If I start doing it at different angles, it may want to turn, but it may have a little bit less of a inclination to turn. And so what we picture is this would be the lever here. And then notice kind of the moment this axis is perpendicular to the lever and the force. So the thing it's trying to rotate around is perpendicular, which is why the cross product is involved. So the moment is going to be given by just the cross product of PQ and F. And then we often want the magnitude of a moment. We just find the magnitude of M. So basically the length of the axis geometrically is going to change based on how likely it is that that thing wants to spin around. So again, it's kind of like work where we did the dot product. Here we do the cross product of PQ, the lever itself, and F, the force being put on the lever, and we'll get what's called the moment, which is the tendency to want to kind of spin around. So I'm going to quickly finish the class. Class is technically over, so if you need to run before your next one, you guys can do that. I'm just going to finish this example, and I can post it and stuff because it won't take very long. But here we have a vertical force of 50 pounds. This is the F being placed on the end of a lever attached to point P, which looks like it's at the origin in the picture. And then we're finding the moment of the force about point P when theta is 60 degrees, and saying all this is happening in the YZ plane. Okay, basically, you can always think of these forces acting in a plane. In this case, it's in the YZ plane. So we need, we need a vector for PQ, the lever itself. It's in the YZ plane, which means X is 0. It has to be three-dimensional because we're going to take a cross product. So I have PQ is 0. And then kind of like we do with everything else, I'm just going to use a unit vector, cosine 60, sine 60. But notice that the lever is 2 feet long. So I didn't leave myself room. So I'm going to multiply this by 2. Okay, this will come out to 0, 1, square root of 3. So that represents the lever. My force is being applied vertically, okay, straight down, meaning I have no X or Y movement. I'm just getting 50 pounds of force straight down, okay, in the Z direction. And so all I do is I do PQ, oops, doing a B, PQ crossed with F. And if I do the cross product, I'm going to have negative 50 minus 0. And then if I go across, I'm going to have 0 minus 0. And then if I go across again, I'm going to have 0 minus 0. Right? If I did the cross product, and I skipped through how I usually do it there, but then this is 50. Would be the magnitude of the moment. This would be called the moment. Okay, so I'll post the video. So I ran through that one a little fast, but that way you guys can run to your break before your next class. And we did finish, but sort of not finish. But you guys have a good afternoon. And don't forget, you guys have a homework problem set. Your first one due Friday. It's only over the last 3 sections, so it doesn't have this on it. This one's on next Fridays. But that's kind of coming up due, and it might take a little while, so don't leave it to the last minute. But otherwise, you guys have a good afternoon, and I will see you guys tomorrow.
Thank you.
Thank you.
Bye, guys.
Thanks, Mr. Smith.
Smith,
Bye.
I have a question.
Okay. What is your question?
Yeah, well, what is the purpose of doing the projections?
The purpose of a projection, so it'll actually end up having a lot of applications, but the main idea for us so far is that you have this force that maybe is like a measurable force. I'm not sharing anymore. I'm on screen. You have this force that's like maybe some measurable force, and you're breaking it down into other components, because maybe, so like in that boat example or whatever, you're worried about the amount of the force moving parallel to the ramp. So the whole point of the projection is if you have this force, but we're only interested in how much of the force is acting. So like for today, I said the wagon, right? And you're pulling on this handle like this, but we only want to know how much of that is actually propelling the wagon forward. We project this thing down, and you can get basically the component that's actually moving in the direction of the wagon and the component that's actually kind of you almost pulling up on the wagon. As you pull at that angle, you might be pulling 20 pounds of force, but 20 pounds isn't really propelling it forward. Some of that's propelling it forward, but because of the angle of the handle, some of it's going actually like pulling against the.
All right, so it's like what we were doing in physics last year.
Yeah,
with,
it'll be similar to physics. You're breaking it down into components that make up that force.
All right.
And the
So the
projection.
only difference is that this is like in the form of vectors.
Yeah.
All right. Thank you.
You're welcome. Have a good afternoon.
You too.